Hi, my name is Joanna Klicka, and today I'm going to be going through Homework 1, Part B. So B1 gives us a scenario in which we are solving for what temperature a container should be raised to so that we meet a certain final pressure. So I'm going to draw out the scenario. So we have a closed container that has 1 kilogram of liquid water at the bottom. Then it also has a vapor phase there that has both water vapor and air in it. So we are giving a couple of parameters. So the first being that the partial pressure of air is 101.325 pascals. We are also given that the initial temperature is 298 degrees Kelvin. We know that the total volume of the container is 0.1 meters cubed. And then we also know that the final pressure that we want is 200 times 10 to the third pascals. So what we are trying to get to is this final pressure. And at that point, the final pressure is going to be the partial pressure of the air plus the partial pressure of the water. So I'm going to break down both the partial pressure of the air and the partial pressure of the water in order to solve this. So first is the partial pressure of the air. So we can turn to our ideal gas law for this. So that is PV equals nRT. And we are interested in the pressure, so we're going to divide by the volume on both sides. So that gives us partial pressure of air is equal to the moles of air times our constant times temperature all over the volume of the vapor phase. So at this point, we have our equation for the partial pressure of air, but we have two unknowns within this equation. So we are going to solve for those two unknowns. So first, we can look at the volume of the vapor phase. So we know the volume of the liquid water, or we know the mass of the liquid water, and we can solve for the volume. And we can do this by using the density of water, which is 1,000 kilograms over 1 meter cubed. So we can take our 1 kilogram of water and convert it over to meters cubed, which gives us 0.001 meters cubed. From there, we can solve for the volume of the vapor by subtracting this from the total volume. So that's 0.1 minus 0.001. And that gives us 0.099 meters cubed. So now we have that, and we'll be able to plug that value into our partial pressure of air equation. The other unknown is the moles of air, so we can look at that next. And again, we can turn to the ideal gas law, but since this time we are interested in the moles, we will divide both sides by the constant and the temperature. So this will give us moles of air is equal to partial pressure of air times the volume of the vapor all over the constant times the initial temperature. So now we know every value for our partial pressure of air equation and would be able to get that value as an output. Next, we can look at the partial pressure of water. So looking at our scenario, we know that we have liquid and vapor water in this container. So we know that at the interface which would be right over here, right at the very top of the liquid phase, that vapor is at the saturation vapor pressure. And we also know that our goal is to raise the pressure from what it is initially up all the way to 200 times 10 to the third pascals. And so when we do this, the temperature will be increasing. And as the temperature increases, some of the sample from the liquid phase will vaporize and become part of the vapor phase. And when that happens, since we are in a sealed container, there's nowhere for this vapor to go, and so the whole vapor phase becomes equal to the saturation vapor pressure. And now that we know this, we can apply Antoine's law, which is log base 10 times pressure equals A minus B over C plus T. Then we're going to get rid of a log, which gives us P equals 10 to the A minus B over C plus T. And so that's your equation for the partial pressure of the water, or the saturation vapor pressure of the water. So we would be good, except we need to keep our units in mind. And when you are using this equation, you want your temperature to be in degrees Celsius. So we've been working in Kelvin, so we need to subtract 273 from our temperature when we put it in. And then it also outputs your pressure in millimeters of mercury, and we want to be in pascals, so we also need to convert that. So if we rewrite our equation to make that happen, you have 10 to the A minus B over C plus T minus 273 times 101325 pascals over 760 millimeters of mercury. And that will give you the partial pressure, or the saturation vapor pressure, in pascals, and you will be able to plug that into our initial equation, which solves for the final pressure. And now we have both components of that equation and are ready to move on to B2. So we can go ahead and take a look at B2. So we're going to explain while implementing in code the nonlinear equation to solve B1. So I'm going to pull up Google Colab. And open up a new notebook so that we can start our code. So first thing I'm going to do is import the needed libraries. So I'm going to import numpy as np, and from scipy.optimize import root. Next, I'm going to take all the parameters from B1 and set them up here. So first we have the initial pressure, which is 101,325 pascals. And we had the initial temperature, which was 298 degrees Kelvin. We were given the mass of the water at 1 kilogram. And finally, we had our final pressure of 200 times 10 to the third pascals. And I'm also going to enter the gas law constant, which is 8.314. So now we have all the variables that we need to go ahead and enter the rest of the code. So like we did in B1, we are going to need to solve for the volume of the vapor phase. So volume vapor, which reminds me that we were given the total volume, which was 0.1 meters cubed. So we're going to need that to calculate the volume of the vapor. So we're going to do the total minus the mass of the water divided by 1,000, because we used the density of water to calculate the volume and then subtracted that from the total volume. So that was one of the unknowns that we had to solve for, and the other one was the moles of air. So we can go ahead and take a look at what that equation was. So that was over here. So that was the pressure times the volume over the constant times the initial temperature. So we can go ahead and enter that over here. Pi times the vapor divide that by our constant times the initial temperature. And that was everything that we needed to solve for the partial pressure of the air. So next we moved on to the partial pressure of the water, which again we determined to be the same as the saturation vapor pressure. And we used Antoine's law, and we're going to again use that here. And to do that, we are going to have to define what A, B, and C are. And since I don't know those off the top of my head, I'm going to go ahead and look it up. So we are going to look up Antoine's law. Oh, there it is. And we're going to scroll down to Wikipedia, where they give us a nice table of values that we're just going to copy and paste over to our code. A value is E, and finally C. So now I am ready to define my function for our saturation vapor pressure of water. This is going to be a function of temperature. And we're going to return the equation that we solved before, this one down here. So that is 10 to the A minus B over C plus T minus 273, my parentheses, we're all set. And then that is going to be multiplied by 101,325 and divided by 760. And again, that was to keep all of our units consistent. And that is all good. So now we're going to define another function. We're going to define, I'm going to call it b2 underscore fun, again as a function of t. And we're going to return that initial equation. So we're going to do bsat underscore w plus, we are going to look at our equation for the partial pressure of the air, which is this one right here. So that was moles of air times R times T all over of the vapor. Double check that I typed that in right. Perfect. And then we are going to subtract that final pressure. It's 200 e to the third, and we're going to do this so that we set the equation equal to 0, because our next step is taking the root. So we're going to go root of b2 underscore fun. We're going to give it an initial guess of 373 degrees. And we were a little bit off, but our final temperature that we would need in order to raise this sample to 200 times 10 to the third pascals is 365 degrees Kelvin, and you are all set. So now we're ready to move on to B3. So B3 gives us another scenario that is very similar to what we just did in B1 and 2, except this time we don't know the total volume of the container, and we do know that there are 0.3 moles of water vapor when we reach our final pressure. So in this scenario, we have two unknowns, so we're going to need two equations in order to solve this. So if we go back to our work from B1, we can see that we already have one equation right here. Since temperature is still one of our unknowns, all the work that we just did to find the temperature is still valid for this. But now we need to find another equation. So I'm going to go over to a new page. And what's helpful for this is knowing that we want the 0.3 moles of water at the final pressure. So what we can do is turn to our ideal gas law, which again is PV equals nRT. And then we can divide both sides by RT to focus on the moles. So we'll have the moles of water is equal to the partial pressure of water times the volume of the vapor all over RT. And so this partial pressure of the water is our saturation vapor pressure, which is something that we already know. So now we have our second equation, and we are all set to go back over to Google Colab and start entering some of this into our code. So the first thing I'm going to do is define our number of moles. So I'm going to put NH2O final, since these are the number of moles that we want when we reach our final pressure, is equal to 0.3. And I'm going to define another function, and this time I'm going to call it B4 underscore fun. And this time, instead of as a function of t, we're going to do a vector, since we have two things we are solving for. And now we need to do v total, comma t equals vec, because those are the two inputs that we are going to have. And then we do need to take some things that were previously outside of the function and put them inside of the function. So these two things are these equations. We're going to insert them here within the function. And the reason for that is that since the total volume is no longer constant, it could be different every time. These need to be within the function because they are dependent on the total volume. So the volume of the vapor directly comes from how much volume we have in total, and then the moles of air directly comes from the volume of the vapor phase, which, as we just talked about, is dependent on the total volume. So now we are ready to, caps lock, return our function. I'm going to put it in brackets since it's a list and there's two variables. And the first one is for the volume, which is our new equation, which we can come back over here and look at. So we are going to do P stat underscore W times the volume of the vapor divided by R times T. And then we are going to subtract the number of moles so that we set that equation equal to 0, and then we will be able to take the root of that. And for the temperature, it's going to be the same exact thing that we did in B1. So I'm just going to come up here and steal that, copy, paste, enter. Everything looks good. So now I should be able to take the root of this function, do square brackets again, and my guess is going to be 0.1 for the volume, and we'll do 373 again for the temperature. And there is your outputs, and now you have solved for the total volume at the point of the final pressure as well as the temperature.